Hi, I'm Casey Collins, and today I want to talk to you about my long term, which is the perspective of a photo. So my question was, how does the angle of a picture change the perspective of distance? So how this question came about was in class when we were presenting our mini long terms. This picture was up on the board, and someone pointed out that each of these red circles mark 10 centimeters on a meter stick. But looking at the picture, the red circles all look different distances apart, when in actuality they're all 10 centimeters apart. And that's because of the angle of the photo. So I wanted to find out if the angle of a camera shot had a relationship between the perspective of distance. So here's some of my claims. There will be an identifiable relationship between the angle of a photo being taken and the distance of an object, whether that is height or length. I also think that it might be possible to determine the distance of an object or the height of an object from a picture if we know the angle of the picture and how far away the picture is being taken. So to set up this experiment, I made a protractor on my floor in my house. So to do this, I marked out 90 centimeters from the wall and just did that all the way around like a protractor, as you can see. And I put a picture on the wall. So in order to do this, I put the camera at each of the protractor spots and pointed it at the center of the picture, and I used a laser pointer to find the center of the wall every time. So when taking a picture of the paper on the wall, I was going to measure in between these two lines, which is an actual distance of 10 centimeters. And I measured each time at this plus sign to keep it consistent, which was also the height of the camera. This is a picture of me making sure that the camera was level. So here's a picture from 90 degrees, which is also known as straight on. So as you can see, the distance between the two lines is a little bit smaller. When I measured it, it was a little bit smaller than actual 10 centimeters. So from 80 degrees, there's a picture from 80 degrees, 70, and looking at those first three pictures, there didn't seem to be much of a difference until I actually measured them, and there was. Here's 60, 50 degrees, 40 degrees, 30 degrees, and 20 degrees. So here's my data. So as you can see, as you move to the right and decrease the angle of a picture, the distance between the two lines shrunk each time. When in actuality, I kept the actual here just to show that it's actually 10 centimeters. However, it appears these distances. Here's my graph of that. It's not a linear function, but it's some type of exponential function. So going off this experiment, I wanted to see if the same goes for vanishing point. And vanishing point is the distance in the back between the two lines as you get closer to a picture. So to do this, I marked out 90 centimeters all the way up to 20 centimeters on my floor and took a picture of the paper on the wall. So here's the picture from 90 centimeters, 80 centimeters, 70 centimeters. So looking at these first three pictures, you can see that as you get closer to the paper on the wall, the distance between the two lines increases. Here's at 60 centimeters, 50 centimeters, 40 centimeters, 30 centimeters, and 20 centimeters. And here's my data that shows that. Again, as you can see, from 90 centimeters away, we had the smallest distance, and from 20 centimeters away, we had the largest distance. So it appears to be the distance between the two lines appears to be getting larger as you get closer to the picture on the wall. Again, I kept the actual here to show what it actually was. And here's my graph of that. Again, it's not a linear function, but it's some type of exponential function, which seemed to consistently drop the same amount each time. So here I wanted to show you the changes between the 2 points with respect to angle. So the difference between a 90-degree angle and an 80-degree angle picture is only 0.1 difference, while the difference between a 30 and a 20-degree angle photo is a whole centimeter difference. So as you can see, as you decrease in angle, the change in the photo, the change in perspective increases a lot more than it does at the very beginning. Same thing for distance away, vanishing point. The difference between 90 and 80 was only 0.9 centimeters, but the difference between 30 and 20 was 4.2, which is a lot bigger. So again, as you can see, it gets a lot bigger as you get closer to the picture. So going off that, I wanted to see if there was a difference between vanishing point with respect to a bridge. So I wanted to find out if you could determine the width of a bridge based on how vanishing point changes in pictures. So my prediction of that was yes. I also wanted to know if you could determine the length of a bridge based on the same thing, and my prediction was also yes. So to set this up, this is for the length test. I used 3 different length bridges. This one was 40 centimeters, the orange one was 47 centimeters, the green one was 30 centimeters, and the red one was 20 centimeters long. So here's my setup. So I put the bridge on close to the wall and marked out 10 all the way up to 90 centimeters away from the front of the bridge. And the first test that I would be doing is the width of a bridge. So here's the width, which ended up being 1 floor tile for the first test. So I'll be taking a picture at the front of each of the tape markers, which represent the distance away from the front of the bridge. When measuring the vanishing point of the bridge, I measured from the very bottom of the bridge, in the back, and the front, as you can see with these red lines. So testing width of the bridge. So I used 3 different widths. The first one was 30 centimeters wide, which ended up being 1 floor tile in my house. The second one was 20 centimeters wide, and the final one was 10 centimeters wide. To keep length consistent, I used the 40 centimeter bridge, which was the orange bridge, the longest one that I had. So here's my data of the 20 centimeter wide bridge. So as you can see, as you get closer to the bridge in distance, the front increases as well as the back and the difference. So here's the graph of the 10 centimeter wide bridge. The blue line represents the front of the bridge, the orange line represents the back of the bridge, and the gray line represents the difference between the front and the back. So as you can see, they all have the same type of function. It's not linear again, and it's some type of exponential function. So here's the data from the 20 centimeter wide bridge. Again, as you can see, as you get closer to the bridge, the front of this bridge increases in perspective, so does the back, and so does the difference. Here's the graph of the 20 centimeter wide bridge. Again, same type of functions as the 10 centimeter one, just a little bit higher Y values because the width of the bridge was bigger this time. Here's the data from the 30 centimeter wide bridge, which again showed the same type of function. So looking at the graph, same type of function, just a larger Y value because the width of the bridge is obviously bigger. So I decided to compare the fronts of each 3 width bridges. So the blue represents the 10 centimeter wide bridge, the orange represents the 20 centimeter wide bridge, and the gray represents the 30 centimeter wide bridge. They all have the same type of function. Again, not linear. So here's the back comparisons. Again, all 3 bridges with 3 different widths have the same type of graph with respect to the change in perspective of the distance between the front and the back. And here's the differences comparison. Again, all three graphs had the same type of exponential function, and they all changed about the same way, with the 30 centimeter wide bridge being the highest Y value. That leads me to testing length of the bridge. So here's the 40 centimeter long bridge, the 30 centimeter long bridge, and the 20 centimeter long bridge. And I kept a consistent bridge width of 30 centimeters the entire time, which was one floor tile. So here's the data from the 20 centimeter long bridge. Again, as you get closer to the bridge, the front increases, the back increases, and so does the difference. Here's the graph of the 20 centimeter long bridge. Thinking back to the width experiment, same type of functions, same type of graphs. They're not linear, but there's some type of polynomial or maybe exponential graph. Here's the data from the 30 centimeter long bridge. Again, showed the same type of data as far as the graph. The blue represents the front, the orange represents the back, and the gray represents the difference. They all kind of increased in the same way as you got closer to the bridge. Here's the data from the 40 centimeter long bridge. Again, showed the same type of functions. So as you can see, as you get closer to the bridge, the front and the back and the difference all get larger, when in actuality, they're all the same length of the bridge and the same distance between the front and the back. It's not changing, but the picture leads us to believe that it is changing. So here's the front comparisons. So there wasn't much difference between each of the three bridges as far as the front comparisons. They all kind of stayed the same as you got farther away from the front of the bridge. Back, they're a little bit more spread out than the front was, but again, they're pretty close and they all have the same type of function. Same with the difference comparisons. So that leads me to my conclusions. So the conclusions I made from this, the overall conclusion that I made is to not make assumptions on the size of something based on how it looks in a picture, because viewpoint can change our perceptions of reality. Again, I also concluded that as you move left or right of an object and increase or decrease the angle that you're taking a picture of, the distance of the object shrinks in perspective. It's not a linear function, but it's some type of polynomial or exponential function. Also, as you come closer to an object, the width of it shrinks. The distance between the 2 points shrinks as well. And that proves vanishing point. It's also not linear function, but some type of polynomial or exponential. Vanishing point has a noticeable change when you get closer to bridges with different widths. So I would expect that it would be possible to determine the width of a bridge by measuring the change in vanishing point as you get closer. Likewise, vanishing point also noticeably changes when you get closer to bridges with different lengths. So I think that it would be a little bit harder to determine the length of a bridge based on how its vanishing point changes as you get closer than it would be to determine the width of a bridge. That concludes my presentation. Thank you. Any questions?